What do a shimmering pearl, a massive underground cave, and a simple cake all have in common? Sounds like a riddle, right? But it's actually a hidden chemical connection that shapes our world in some pretty surprising ways. In this explainer, we're going to uncover the chemistry of carbonates and see how one simple molecule connects these three seemingly unrelated things. Okay, first up, we have a pearl. It's this beautiful object formed layer by tiny layer inside a living creature. Just a perfect example of nature's artistry at work. All right, now let's go from the ocean to deep inside the earth. Here we see these massive, ancient stalactites formed over thousands and thousands of years, drip by painstaking drip. They're like nature's own cathedrals, carved right out of stone. So, two incredible but seemingly unconnected natural wonders. And for our final piece of the puzzle, something you probably have in your kitchen right now, a simple box of baking soda. You know, that humble powder we use all the time. So a pearl, a cave, and a box of baking soda. Three completely different things, right? But what if I told you they are all connected by one single, powerful chemical building block? So what is this hidden connection? Let's find out. The answer to our puzzle is a tiny but incredibly powerful molecule. It's the unsung hero that links the ocean floor, the deep earth, and your kitchen counter. And it all comes down to one thing. Meet the carbonate ion. It's an anion, which is really just a fancy word for a molecule with a negative charge, made of one carbon and three oxygen atoms. This is the chemical hero that connects everything we've just seen. The calcium carbonate in a pearl? Yep, that's our ion at work. The very same compound in a stalactite? That's our ion again. And the sodium bicarbonate in your pantry? You guessed it, it's all about the carbonate ion. But the carbonate ion doesn't work alone. It has a close and versatile relative that's just as important to our story. So let's meet the two key players in the carbonate family. On one side, we have the carbonate ion, the foundation of our story. It carries a -2 charge, which makes it really eager to bond with things. And on the other side, we have its sibling, the bicarbonate. See that extra hydrogen atom? That simple little addition changes its charge to -1 and, as we're about to see, it completely transforms its personality and its chemical abilities. So where do we find this chemical family? I mean, everywhere, from the vast limestone mountain ranges that make up huge parts of our continents, to the delicate shells of mollusks and the pearls inside them. They're even mined from the earth in minerals like trona, which is a major source of sodium carbonate. This family is truly all around us. Okay, but what if you can't just dig them up? Well, chemists have a pretty clever way to make them. They start with a common metal compound, like an oxide or a hydroxide, and they react it with carbon dioxide gas. The CO2 gets absorbed and poof, a stable carbonate salt is formed. It's a really fundamental reaction that's used to produce carbonates on a massive scale. Now let's go back to those incredible caves. The story of how they form is such a powerful example of carbonate chemistry at work on a geological timescale. It's a story of both creation and, well, dissolution. It all starts with rain. As rain falls, it absorbs carbon dioxide from the atmosphere, becoming just a little bit acidic. Now, when this acidic water seeps through the ground and flows over limestone, which is just solid calcium carbonate, a really remarkable reaction happens. The acid slowly dissolves the rock, transforming the insoluble carbonate into a soluble bicarbonate that gets carried away by the water. And over millions of years, this process carves out these huge underground caves. But here's where it gets really cool. What chemistry takes away, it can also give back. When that bicarbonate-rich water drips from a cave ceiling, the water evaporates and the carbon dioxide is released back into the air. This reverses the whole reaction, turning the soluble bicarbonate back into solid calcium carbonate. And drip by drip, over centuries, that deposit grows into a magnificent stalactite. It's just a brilliant example of how the exact same chemistry can both carve and build. So, carbonates can build mountains and carve caves? I mean, that's pretty impressive. But their power is just as evident in our daily lives, from our medicine cabinets to our kitchens. Let's see how this powerful chemistry shows up in our everyday world. If you've ever had heartburn, you've likely relied on carbonate chemistry for relief without even realizing it. That chalky little tablet you take, it's made of the exact same chemical as limestone and pearls, calcium carbonate. So how does it work? Well, your stomach is full of hydrochloric acid. The calcium carbonate in the antacid is a base, and it reacts with that acid. This neutralization reaction turns that harsh stomach acid into harmless calcium chloride, water, and a little bit of carbon dioxide gas. And yes, That's exactly why antacids can sometimes make you burp. Okay, now let's head over to the kitchen, home of our third and final mystery item. That box of baking soda is pure sodium bicarbonate, our versatile friend, the hydrogen carbonate. Its magic lies in the same principle as the antacid, an acid-base reaction. When you mix baking soda with an acidic ingredient in your dough, like buttermilk or lemon juice, they react to produce bubbles of carbon dioxide gas. The dough traps those bubbles, causing it to expand, and that's what gives your cakes and breads that light, fluffy texture we all love. Now, here's what's really fascinating about bicarbonate. It has a secret identity. In baking, it acts as a base, reacting with an acid. But, and this is what makes it so useful, it can also act as an acid, reacting with strong bases. This dual nature is called being amphoteric. It can donate that extra hydrogen atom, which is the definition of what an acid does. So it can neutralize an acid by accepting a proton, or it can neutralize a base by donating its own. This incredible flexibility makes it a key ingredient not just in baking, but in everything from water treatment to pharmaceuticals, where it's used to precisely control pH levels. So, from planetary geology to the biology of a mollusk, and even the food on our tables, it's clear these compounds are way more than just simple chemicals. They are fundamental players in the world around us, shaping it in countless ways. So let's recap. Carbonates are nature's artists, sculpting landscapes over millennia. There are practical household helpers, making our food taste better and our bodies feel better. And they are the workhorses of industrial chemistry, used in everything from making glass to synthesizing other chemicals. Simply put, they are absolutely essential to our world. And to put their importance in perspective, of all the carbonates in the world, just two, sodium carbonate and calcium carbonate, are used in the largest quantities commercially. Their impact on our global economy and industry is absolutely immense. So the same simple ion connects the vast and the small, the ancient and the everyday. It builds worlds and bakes our bread. And that's the real power of chemistry, finding these elegant hidden connections. It makes you wonder, doesn't it? What other invisible chemistry is hiding in your world?